Okay, welcome back. We're going to do our second round of the deep version of perception today. So last time I gave, I'm sorry to have given a whirlwind overview of deep learning. It's actually, I really want your feedback on that, because my thinking was that I would try to give a version that people who didn't know much would understand, and a version that called out to some other more advanced topics. I hope I didn't land in the middle and everybody hated it. But please give me we're going to put a specific question on that, on the survey about that, and help me figure out how to dial in the first lecture on deep learning. It's a big ask for me. Good. Okay. But today we're going to slow down and we're going to talk through a couple more specific algorithms, ideas that connect that pipeline with the things we need from manipulation that maybe we don't need in a standard computer vision world. So let me put it in context by thinking about the system that we sort of built last time. If I have my block diagram with my manipulation station here with all my output ports and everything like this, right? And some of those output ports that are most relevant for today are the RGBD sensors. And we've got some perception system, which is now, let's say, a deep neural network. And we're eventually going to get over to our planner, like we wrote for the clutter clearing example, and then our controller. And we ultimately want to send commands back into the low level of the station. There's actually even additional layers of control inside here, right, that are doing joint impedance control. But we had differential IK, for instance, in this block here. And the connection between the planner and control, I guess the example we've talked about the most so far is sort of well understood. We said we're going to send gripper trajectories. We're going to spool them out over time and ask our controller, if this is the diffIK version, to turn those into joint commands that the manipulation station knows how to execute. The question really is, if we have this immense pipeline from deep learning, and that can work more natively with RGBD inputs, then how should we go from here over to the planner, right? What is the information that we most need for manipulation? Now, we can be ambitious with our ideas here because, as we talked quickly about last time, one of the most amazing things about these deep learning architectures is that I can potentially, even if I have a task that's pretty narrow and specific to my robotics application, there's a chance I could pre-train on image classification in ImageNet, and then with a small amount of data, train a more relevant downstream task. Okay? So the big question is, what's the right task? And let me distinguish this. Well, later in the class, there is a version of this that goes from RGBD through a neural network straight to control, or straight to the manipulation station. Let me just make it the extreme version, which would be pixels to torques. Okay. We'll do this later. That's a good idea. I think there's lots of good things to learn about that idea. But that's not what I want to do today. What I want to do today is embrace the fact that we have a beginning of a pretty powerful tool chain for these layers, and we're going to have more to develop in that space. And there's just this huge power of tools that we already have in the community, and we just need to figure out the best way to talk to it, to get from our rich camera input, our rich environment, into something that is sufficient to describe the task and consumable by our planning and control algorithms. Okay, so the big question is, what are those useful representations? And there's not one answer. There's not a right answer. This field is changing every day, but there's some good ideas that have emerged, and I think even just picking one or two of them and going through them a little bit carefully, hopefully that'll encourage you to read more and think more about even more of them. So the answer I gave yesterday, or from Tuesday, was we're going to take our RGB in, come out with our instance segmentation, and then go through one more step, for instance, maybe ICP, for instance, and turn that into the estimated object poses, which I can then send to my planner. That was sort of version 1 we talked about, leaning heavily on instance segmentation. We also said you could take the same thing and enable a different planner that maybe in the middle here if we just do our antipodal grasps. Right, so maybe if this is still the instance segmentation, here we could still do this and come up with some desired grasps and send that to my planner. Okay, so those are two things that we, if we just use the out-of-the-box computer vision tools, Mask-R CNN for this, then we already have some potential pipelines. And of course, for both of these, there are versions of this where people would recommend that you just go, all the way here as a neural network. Just try to hop over that, or maybe go all the way here as a neural network. Those are certainly possible, and I'm going to try to write up a fairly, succinct, but kind of a summary of what are people doing in deep pose estimation. This would be, if I did this, that would be the world of deep pose estimation. And there's a lot of good ideas in there. And this would be maybe, let's say, deep grasp selection. That's my name. There's a bunch of known algorithms for that. I'm not sure there's one really good overall name, but. Okay, both of those are possible and are good ideas. But I want to stop and think, is this even the right interface? Is this notion of putting the pose being the summary of everything that my perception system sees being the right interface to the planner? Okay, so remember, we get to be aggressive here. We can train our network on almost anything, right? Is sending sort of estimated object poses the best signal? Is that the best connection? And there's a couple reasons why it seems maybe we can do better, right? The first one is I would say this assumes a lot about having known models. Right? If I have a model, then, and the world is not moving, then telling me the pose of the object, or maybe all the objects in the scene, is everything I should need to know, right? In some sense. It is, well, it's a complete description of the current state of the world. That's a slightly different thing. Maybe in the full glory, I would also want, assuming the world is nicely second order, maybe I'd also want the spatial velocity of that object. Okay, but if I have known models, then this is actually a reasonable thing to do. There are still limitations even in that case. But we're going to try to overcome that assumption today a bit. For the first time, we're going to try to start doing manipulation of at least categories of objects. Okay. The second thing that I don't like about using pose anymore in this case is it's actually asking for more than we can potentially get, right? It might be asking too much. Okay, so for instance, if I have partial views of an object, maybe it's actually very hard to estimate the perfect pose, right? Especially if there's symmetries. Those would be a classic case where maybe the pose isn't the naturally right description. And it might be more than I need for manipulation. Okay, so I'm going to try to make this case in a story in just a second, but just to set it up at the high level here. And I would say the third thing about it, that it seems like a major limitation of just using pose as our language from the perception system, is that by itself, just saying that I have a nominal estimate of what the object's pose is, isn't maybe sufficiently rich in the sense that it doesn't tell me anything about the uncertainty from the perception system. Okay. And we should try to describe uncertainty, right? I'm going to try to use this as a theme as we go through, but this pipeline, actually, the mask-RCNN pipeline, did talk about uncertainty. It was a little hidden, right? But the fact that every classification, every potential bounding box had a score function that was between 0 and 1, right? And the ones it was confident in was close to 1, and there was one that was ridiculous and it was close to 0, right? So it told me something more. It told me I have some segmentations, but I've got a limited confidence about at least one of them, right? So maybe we need a language to talk about that in the language of pose, or maybe we need to just think about other representations completely. Okay, so let me tell you, about this in the case of an example, right? So this is the category level manipulation version of the story, right? So we want to do some sort of manipulation, but we want to do it not on known objects, but objects that are all from the same category, okay? Is that clear, right? So it's an interesting question immediately to say, I know something about mugs. I could imagine writing a program that would work for all mugs, but if the perception system only told me the pose, then I don't even know what the pose means for those, right? And it's also a good example that I don't need to know the pose perfectly to accomplish a lot of interesting tasks with mugs, okay? Okay, this is the category level manipulation problem, right? Imagine mugs, it turns out that the field that's working on category level manipulation have all roughly converged on mugs or shoes. Sometimes you get a plate, or you have bowls, right? I mean, there's like a really small set of categories that everybody really likes to talk about. So you'll see mugs and shoes throughout from different papers, okay? And it's an interesting problem because it is a rich class of, I think it's like the Goldilocks place between, I don't want to assume I have known objects, but I don't want to have to deal with arbitrary objects, right? So like, tell me it's a mug. The mugs have a handful of, we can generate arbitrary mugs that are interesting. You can also find mugs at the Disney store that have, ears and or cow udders or something like this. So you can go as far as you want away from the nominal mug. But there's a really nice problem to just say, how would I write a manipulation system that could deal with that level of variation, not the whole shebang, anything, okay? I think it's a really nice sort of intermediate. It's actually pretty cool that you can have these simulation pipelines that will just take a few parameters, kick out a CAD file. There's procedural CAD is a thing now, right? You can take a texture map, slap it on your mug, right, and generate like all kinds of mugs, right, in simulation. Harder to do with shoes, but mugs are pretty good. We have done vegetables, procedural potatoes. Really. Okay. So, so how do you think about this sort of pose estimation problem at the category level? There's a couple, like the first thing that people would think about in computer vision about how to do this would be maybe there's a famous work called NOX, right? It's this normalized object coordinate space, NOX, all right? Where you take a whole category of objects and you try to come up with some canonicalization, something that would make it so that if you tell me the pose of this canonical object, then I can relate that to the thing I'm seeing right now, so that pose is still a meaningful quantity. Because if you don't have some notion of how to go from an arbitrary thing, like what is the center, at which point am I talking about the pose, even though that point might be in different places on different cameras, then you don't have a full representation. So this is an extremely good way to do it that has been successful in computer vision. And there are ways to think about category level pose estimation. But I want to also talk about this uncertainty, okay? And I just say that there's more challenges that come up if you really want to use pose and carry it through your entire pipeline, okay? In particular, like what is the right way to represent uncertainty in pose? And I'm sorry that it's become a theme, but once again, the thing that screws everything up is the representation of rotations, right? How do you write uncertainty around rotations? For positions, you can imagine just using Gaussians, and that's sort of fine. You can hire moments if you want to, right? I could say I have a Gaussian uncertainty around the position of my object. But for the rotations, you need something more clever. There is something more clever. There's a language for this. It's called the Bingham distribution. And I want you to know that it is possible, and there's a natural Gaussian in the space of rotations, and it's done by taking a Gaussian in the higher dimensional space and then projecting it, and then intersecting it, onto the unit disk. So this is the 2D version where it's easy to visualize. I've got just a Gaussian there, and I have the intersection with the S1 here. But the place where we want to use for 3D orientations is to think about how do I put a distribution over possible unit quaternions on a 4-dimensional sphere, okay? And it looks like this. I just want to open your mind to the fact that these kind of things can exist. That actually a Gaussian on a quaternion sort of makes sense. It's just called the Bingham distribution. Okay, you can write the intersection of a Gaussian with the 4-dimensional sphere, and you get beautiful representations. This is kind of the right way to do Gaussian-like things on the quaternion space. Okay, where small distributions would be, you just have the antipodal pairs show up, right? And then as you widen it, you remember the quaternions are always antipodal, so it's going to be symmetric along that antipodal axis there, and you can get full rings of uncertainty and the like. And I think you need to do this. If you want to use pose everywhere in your system, and you want your perception system to be able to say it's uncertain about things, you need to do that. I mean, mugs are actually a great motivator for that. If I see a mug in the kitchen sink, right, and if I can see its handle, I might be able to give you the pose with a very small uncertainty estimate. But what if the handle's on the back side? It would be just wrong to choose any one of the possible orientations without somehow saying it could be any of these, right? So having distributions over pose is a thing you can do, but it gets hard fast. It gets very hard fast to carry that all the way through. And the types of distributions you get with partial views and occlusions are probably non-Bingham pretty quickly. There's a pipeline you can exercise, but I don't think it's the best one. It's not the one that I would fully advertise. Okay, so here's a different, just to give you a version that's a different answer to this. What if instead of using pose, we just talk about a handful of points attached to the body or in the coordinate frame relative to the body? This is our first proposal for an alternative representation at that level. Let's think about key points. Okay, and the key points I'm going to talk about now, if you're familiar with the key point literature, this would be, I'm talking about the semantic version of key points first. Okay, so roughly speaking, what if my RGB or RGBD in goes through some sort of perception module and outputted a list of XYZ positions for key point 1. My claim is that I'm going to try to argue over the next few examples here, that actually is a pretty natural way to talk about a lot of the category level problems we have. It assumes less about the known models, right? It does surprisingly well thinking about partial views and symmetries. We'll talk about that. And it has a nice connection to uncertainty. Even more, it turns out it's actually really pretty useful when you hand that to the planning. It's a pretty natural representation to think about writing a planner around. Okay? So this is just the first example of a different representation we could use as the output of our perception system. Okay, right? So it comes from, key points are a thing in computer vision. They started off with these open pose kind of, people dancing. You want to track the dancing people, right? And so the way they do it is they put key points on the hands and the elbows and the shoulders and make a skeleton out of that and track it. It's incredibly impressive. Okay, it works really well on novel videos and things like this now. So the proposal here is let's take our mugs, and instead of trying to represent a canonical pose for all possible mugs, let's pick a few canonical points, just a few of them maybe, right? Maybe the bottom of the mug where it's on the table, maybe something that says what's the top of the mug, just so I have a sense of maybe the bottom should be below the top, that's useful. And then depending on what you want to do, maybe you can put a key point in the handle if you want to pick up the mug and, in this case, hang it on the rack. That's another favorite, yeah? Hang the mug on the rack, okay? Then in order to do that, we'll work through it, but you can actually write that task pretty nicely as a planning problem where you just know what the location of the yellow dot is, right? You don't actually have to know the absolute pose of the object. And we'll argue, like I said, it fits more naturally into this framework. Okay, so here's the basic idea of how it's going to fit into that planar framework, okay? So imagine that the output of this, I should even use my multi-body notation. So what I'm going to imagine is that this outputs the position of key point 1 in the world frame here, and key point I, for all I. There's a pretty simple assumption we could try to make. The first assumption, just saying, I'm going to reach over, I'm going to grab it. Once I've grabbed it, I'm going to assume that those key points, because if I've sufficiently grabbed the object, are going to move with my hand, rigidly with my hand. and then when I release, they'll stay in the world, right? And we should pick manipulation actions for which that's true. If I tried to grab over here, that's not going to be true, but with a little bit of a few assumptions about, pretty reasonable assumptions, you can imagine that the dynamics of these key points could be such that when my hand is open, then those key points aren't moving. And when my gripper is closed, then what I'll just assume that the position of the key point relative to the gripper frame is constant. That's the only difference, right? And if I do that, then I can imagine coming up with a sequence of these plus the open and close that could schedule me to move my key points around in the world. Yeah? I'll plan to go over and pick it up, close, and then I'll start the key points moving along with my hand, and I'll drop it off. Off we go. Okay, so it turns out actually it's a pretty rich specification language. It's even more rich, especially, so the versions we've talked about so far have been, I had a desired pose exactly of my hand at the end, or my key points at the end. You won't be surprised that when we get to motion planning, we're going to loosen that up and be able to write objectives and constraints on the potential key point locations. Okay. Okay, so to execute that, the key points are most of what you need, but they're not quite enough, right? The key points will let me write my planner for the most part, but I do need to have some notion of where to grasp. So different people address this in different ways. So Anthony's got a version where the key points, he's got key points for the grasping too, and a dense enough key points that he can find a grasp that will in the language of the key points, roughly, in his neural descriptor fields. But you could also, in a simpler case, maybe just use the raw point cloud and do your antipodal grasping in the vicinity of the key points, right? So just, if I have the top center, and maybe I have the ability to segment, because I've got my mask RCNN, then you can imagine, choose your grasp on that object, but then plan the motion once I'm in that grasp in order to move the key points around. And that works incredibly well. There's a few things that I think it's worth saying about how you make these tools work. People have questions at that level? How many people know key point type algorithms? Yes? Used them? Okay, good. I can see both. And an and in the middle, that's good. There's a few important things to know about them, and knowing them will help us understand, for instance, how you think about uncertainty in the language of key points. There's a few famous architectures, neural architectures. I won't dwell on them. Architectures. There's a convolutional pose machines is one of the first. I'll link to them in the text. The one we've tended to use is the integral pose machines, or the integral version of that. Which is a small change on the original architecture. Okay, but there's a key feature that both of these have that you should understand, which is that I take my RGB in, and I don't actually directly regress the key points. What I put out here first from the neural network is a heat map. For instance, in the simple case, let's just take RGB and have a 2D heat map come up, and I've got a figure for this in a second. Okay, and then afterwards, I'll find most often the highest value, the peaks, in my heat map in order to put out my. Okay, it's an interesting idea. You know, it's one of these things that it makes things more differentiable, and it tends to be a more robust metric for neural networks. But so the key points are probably impossibly small to see, but there's little red dots here. I didn't think about the screen resolution when I picked this particular image. Okay, there's little red dots on the faces that are picking nominal key points on a face. People do this for, you know, for face tracking, by the way. They'd actually have like pretty dense, you know, they have a key point for every sort of part of your face, for your lips, for your eyes, right? And it's kind of spooky to see the points being plotted around. This one's just plotting like 5 of them, one for the left ear, I think is this one, in each of those pictures, okay? And the heat map is the ground truth heat map that people would use, would say that if I know the key point is in a particular location, here for the left ear, then I'm going to draw just a Gaussian bump centered at the known heat point location. That's the standard thing, and have it basically effectively 0 for most of the image, but just have this narrow Gaussian bump. And your goal is actually for every point you're trying to estimate to predict an entire image which has the peak at that value. Right, so this is the heat map representation. Now you can see quickly how that could encode uncertainty in a nice way, right? So if I was confused about which was the left or the right ear, maybe I'd have a second small hill over there in my output of my network. And that allows you to then, if you wanted to do more robust things down the line, reasoning about the uncertainty, you could leverage that richer representation. The fact that it's a Gaussian of like known kernel, that bugs the snot out of me. It's total hack, right? That you know, people just, I think, do kernel hacking on that. It doesn't seem particularly principled to me, but it works well in practice. So just admit that. Okay, but this is sort of a nice representation. How do you train that? Well, you can, of course, click on key points, have humans label key points in a lot of different images. And then for every click, you make a little Gaussian desired image and you train your network. Yeah? There are, of course, better ways in the manipulation workflow. We can play the same kind of trick we played to label our segmentations. You could take an object that you don't even have a model of. You could spin it, or spin your camera around it, make your NeRF or somehow your dense reconstruction of it, and then click once for each key point on the reconstructed model, and back project to have labels for all of the possible images that came in. Right? That's a really fast way to generate a lot of labeled data for key points. And that works pretty well, right? So this is the way that we then, this is the shoes example, right? But if you want to sort of manipulate any possible shoe, right? This was a great demo. I remember we had this running one day during visit day when the new grad students came to the lab, and then they were coming into our lab space to eat lunch, right? And so we basically asked everybody to take their shoe off, which was maybe not the best hosting I could have done, but we got a huge variety of shoes to test that day. And it picked up almost everyone. It was like incredibly good. It was just, boom, put the shoe on the rack, put the shoe on the rack. And then Daniela, our lab director, Daniela Roos, came in, and she had these ridiculously shiny black Italian shoes, and we couldn't do it. And I was terrified of hurting her shoes, by the way. So that was the one we failed on. Gretchen actually also had some high heels that we had never seen before, but it's all good. We added them to the training set, and now we can do it. Now we can do those high heels, right? So it's surprisingly powerful and simple sort of pipeline. You can, of course, also generate key points synthetically, right? If you have a distribution of objects, if you have your parametric mugs and you want to just generate a bunch of different labeled key points, then you can generate synthetic images, and that's a super powerful pipeline, right? So we did a quick example of it on boxes, because this was when Greg was during the pandemic, and he was walking past the lobby of one of the dorms and seeing piles of boxes. He's like, that's a pretty good data set. So he would just start collecting images of the front lobby of the dorm and generated a whole category level of boxes, right? But he also did this amazing job of using Blender rendering to set up the procedural models. So it's not too hard to generate boxes of different size, but it's a little hard to see, but it's incredibly close to photorealistic. He took a handful of texture maps of different boxes that he saw in the front lobby and generated just these huge data sets of perfectly labeled boxes that looked pretty realistic, right? You can get the ground truth instance level pixel-wise segmentations, but you see the ground truth key points. It's super relevant and interesting to know that you could train your key point detector to predict. You don't have to pick only visible key points, right? You could choose to predict key points that are occluded, right? If I look at that image on a brighter screen, I could hallucinate for myself and give you an estimate of what the back corner looks like, even though I can't see it. And if I can generate training data that puts a mark in the back corner, which both of those two pipelines I suggested couldn't do, then you can still ask the perception system to predict even occluded key points. Okay, so that's pretty powerful. Almost always, these, this was a little too simple. Almost always, people will run it through a mask, a segmentation pipeline first, so that the key point network has to only work on the segmented point clouds, maybe the bounding box that comes out of mask-RCNN. I assume you could do it on the big image, and it would be okay, but it tends to work better if you give it the scaled and cropped version, zoomed in version. And then this is the detections on his raw data in the lobby. His predicted key points, where you can see like the heat maps and various levels of uncertainty, right? The fact that those are spread out and not as peaky is important information. It's sort of frustrating that, although it's obviously important and good, the back half of our tools a lot of the algorithms we'll talk about in class don't actually know how to reason about that uncertainty. It's an advanced topic to reason about uncertainty in your planner and your controller and the like. We'll mention it. Well, I think we'll have at least one lecture on it towards the end, but there's no question we should be asking our perception system for it. I think there's work to do in how to consume it. Okay, so that's pretty good, and those are the ground truth key points that were labeled. Yeah? Questions about the key point pipeline? Did I make the point of how it works for a whole category sufficiently well, right? It's easy to label sort of the toe of any shoe, the heel of any shoe, the top of any shoe, but it's harder to talk about a canonical pose of every shoe. There are people that really don't like key points as a representation. I'm not trying to say this is the end-all be-all, but it's surprisingly simple to think about and good. Right, and we did demonstrations back then of understanding how many trained objects and finding every mug we could buy at on Amazon, and it's pretty darn robust. There's also nice additions to it, right? So if you think about what that pipeline couldn't do right out of the box, so if I just used the initial point cloud to decide where I'm going to grasp, and then I just think about where those key points are going to move in space, the fact that the key points are not a complete representation of the geometry, we had to be fairly conservative so that we didn't like crack mugs on the table as we went around. We had to pick fairly conservative trajectories for our key points. Okay, but you can put this together with other deep learning, tools. For instance, if you just imagine the missing part of the point cloud and have a completed shape of your object, then you could put the entire geometry moving through as a constraint in your planning system, and that added some richness to what we could do. We could do more realistic collision avoidance constraints. Now this one's pretty cool. People also talk about learning oriented key points, where you have not just the XYZ location, but maybe the axes, the three-dimensional coordinate system. If you do that, and you just know what is the key point and axis on the object I'm manipulating, that turns out to be enough to do interesting control with, right? So if you wanted to regulate the force at the end effector of a screw or an eraser or whatever, then you can write a controller making the same assumption that the object becomes rigidly attached to my hand when my hand's closed on it. I can start regulating my forces of my hand at the point defined by the key point and with the orientation defined by the key point, okay? And that's enough with that pretty simple pipeline to do some pretty cool stuff, right? So Wei was able to pick up various Lego blocks, insert various USB keys, do mating, with all of those are sort of force-sensitive type tasks, putting Lego blocks together or putting USB in, right? And you could do that with very little knowledge of the object by just understanding its geometry at the level of a key point and applying these tools. Seems only there we go. Right, so you get any possible eraser. You want to be able to apply a wiping motion on the screen, and the controllers that we'll talk about more soon are enough to regulate the forces, pretty well. Yes, please.
Do these key points assume sort of they're rigid relative to one another?
Awesome. So what are we assuming here, right? So we are assuming that key point 1 versus key point 2 is fixed given the initial observation, but it's not fixed to some canonical model, right? So my model does not assume that I know this a priori, but we assume that they are rigidly attached, they rigidly move through space.
So in the case of you have the key points for a canonical shoe, but when you see a new shoe, they can move around a little bit relative to one another, but then for that particular shoe, they're fixed.
That's right, exactly right, yep. Yep, perfect. There's versions of this that people have done. I mean, that David Held's lab, for instance, has done that use key points or other particle level representations that do this for deformable objects, for instance. There are definitely extensions like that. But the simplest version is just assume they're going to stay rigidly, move rigidly. Good. Other questions? Yeah? It's a surprisingly powerful pipeline, I'd say. One thing that people don't like about the key points, I remember when we did those demos, for instance, the thing that every single person asked, they're like, but you hand label the key points, right? You're going to learn them next, right? Learn the key points, right? And I took offense because I actually think at some point the human has to say something about the task. And I think this is, in my mind, the key point is like a minimal amount of information to ask the human that defines the task. And I think that's true. I think there's a role where you have to have semantic key points, where the human applied some amount of semantic information to this is the handle, I want you to pick it up here, right? But there are also ways that you could use key points where the semantics aren't important and they're really just a summary of the geometry. And in that case, I think people have done beautiful work on learning key points. And so you can, for instance, self-supervise and try to find ways to label key points. One of the best examples, I think, of that is this Keto work of learning the key points that were relevant for some forceful manipulation type tasks. Okay, so learning key points is absolutely a thing, but I think if you do learn them, you don't get to call them a label. You don't have the human-informed knowledge attached to them. You don't have the semantics attached. Okay, but it's absolutely a thing. Okay, so you can actually take that idea even farther. and think, why am I just doing, this is sort of like the sparse key points story, right? There's really no reason to make them sparse. You can go ahead and try to learn dense key points that cover all over the entire geometry. And if they're, if they're consistent, then they take on a different sort of notion here. So there's another representation that's called dense object nets. And I'll tell you some of the details of this one too. This was a very enabling for us, right? So here's when I show you these pictures, this is what I hope you see. So in the left, we have a canonical image of the object and the task, the object in this case being a MIT hat, okay? We have someone holding their mouse over the object at a particular point and maybe moving it around to make the demonstration interesting. And now we're seeing a different playback. And the goal here is to find the associated key point, if you will, in the hat in the other frames, right? So this is also called dense correspondences, right? It's exactly the same as we meant by correspondences in the ICP pipeline, right? And it makes total sense to try to learn correspondences. Remember in the ICP loop, once we knew the correspondences, extracting the pose was easy, if that's our choice, or maybe we don't want to do it, right? So it makes total sense that if you try to solve the hard combinatorial part of the problem by learning from trial and error, right? And then allow additional tools to sort of work from there. So asking now, as a different representation now, not just sparse key points, but dense key points is I think really powerful. Is that image clear? I'm going to show a bunch of them, so I hope it's clear, right? So you can see the uncertainty there, right? But the big thing that changed is this is not n, sparse key points here. We could put this over anywhere on the hat, and for any possible place on the hat, we'll show you a distribution of possible correspondences. Okay, so let me tell you a little bit about how a standard correspondence network would work. Now, when we're going from every pixel in the original image to every pixel on the final image, we're not going to use, for every possible key point, its own heat map. That would be the logical extension of this, but it gets pretty expensive. So we're going to do a slightly different representation here, based on some of the ideas from self-supervised learning. So we're going to take RGB in, put it through our neural network, and the thing that we want out is a descriptor image. Okay, whereas if this thing was a RGB, it has some width by height by 3 channels, right? So I've got, see what I'm saying? It's width by height by 3. It's a tensor, but each color channel is an image of width and height, and then there's 3 of them, R, G, and B. And then this one, I'm going to put out a different image that is colorized, roughly, in this arbitrary extra dimension of descriptors, right? So I'm going to map every pixel in my original image to some descriptor space. I don't know what that space is going to look like exactly, but I'm going to ask it to have certain properties. In particular, that it satisfies it gives correspondences. That same, if I have 2 images where I know I have the same point on the object, then they should arrive at the same place in dense descriptor space. Okay, So D, when I draw these pictures, those pictures like that, we chose D to be 3 so that we could render it as an RGB image, okay? But you can choose D to be higher, for instance. It doesn't have to be just 3. And then this is trained Siamese style with self-supervised learning. Okay, so we take 2 images that we know have the same points in them. I'll show you the pipeline in a second, but we're going to do that same dense reconstruction trick and know from 2 different images that there's a point on the geometry that if I back project, it should be the same point in both of those images. And then there's a bunch of points on the object that should be different points, right? So I'm going to put 2 images through my neural networks. My dense descriptor net. Get my other image, okay? And I basically give positive reward, for matches in descriptor space, right? And I also have some negative examples. I do some non-negative mining, hard negative mining to say this is a non-match. Okay, so start off by making the robot move around. You come up with a dense reconstruction. And then for each point on this image, for each point on the caterpillar in this case, this is a plush toy that we got. It has lots of interesting buckles, and so we thought it'd be good for learning manipulation, but we ended up just using it for perception. Everybody wonders why we have this strange caterpillar in the lab. Okay. But we take all those images, and this time it's deformable. Okay, there's no rigidity assumption here, and then we say this point here, which I know to be in a different frame, the same point, that should arrive in the same place in descriptor space. So we write loss functions like this for matches. We say that we want some average of the neural network output from image A at a known location A minus the neural network in image B at the known correspondence B, where UA is known to correspond, match with UB, right? I minimize that loss. I normalize it over the total number of matches. Okay, and then I take a bunch of non-matches too, and just play a little trick. It looks like the opposite of this roughly. That says I want points that are that should not be the same to have a large distance in this space, right? Up to some threshold. And you sum those 2 together, and you get your pixel-wise contrastive loss. There's a bunch of tricks that people do to make this work better, right? You tend to like for instance, normalizing so your descriptors are on the unit sphere. That seems to be a good idea. Data augmentation is absolutely a good idea, right? People do background domain randomization as a particular form of data augmentation. All those tricks that people do in similar pipelines are applied here also, okay? And then what you get out here is, you take your caterpillar. Even though it was stationary when we scanned it, there's nothing in the network that requires it to be rigid. And what you want to see here is that the colors, which is our 3D, when we choose D to be 3, and we draw them as an image, that as you move the caterpillar around, you want the same points in the caterpillar to roughly come up with the same colors in all the frames. And it's like surprisingly good. Okay, we have a Baymax doll in lab, and it's surprisingly good. Okay, we had various, this is now the same demo again, where the mouse is over this, right? And this is the old version. This was the new version, where we got much tighter predictions by playing some of those extra games about normalizing the descriptors and things like that. And it's surprisingly good. Like you can go down left leg, right leg, and it gives you a distribution of possible key points. If you wanted to extract a particular key point out, you can of course say, there's a descriptor here, what is the peak value of my uncertainty map in the other image? That's an operation that's natural to do and can be done differentiably, for instance. But it turns out that this is something that we didn't actually have any reason to expect. But if you train it on a bunch of different hats, then somehow we also found that the dense descriptors, I mean, this is actually, I would say this is a limitation. It worked and we exploited it, but we don't understand it well enough for it to be a reliable thing at the time. But it turns out that it somehow learned a category level descriptor. Okay, we trained on a bunch of different hats independently, and then we could put it on one hat. It tells us the correspondences on all the hats. Right? Something about the fact that it can only fit the way it fits things in d-dimensional space somehow made this happen. If you want to learn different hats independently, you can. That's what this other side was doing. You just have to train with all the hats in the image at the same time. And if you're specifically saying don't match this hat, the point on this hat with this hat, then it will learn not to. But given without that pressure, it somehow seems to pick points that are somehow geometrically related across different objects in a category. So think of that as a dense self-supervised key point, right? There was no human labels anywhere in that pipeline. We scanned the object, it did its thing from there. And that alone, depending on what your pipeline needs to be after the fact, right, that's actually alone to do some interesting things. So if you just say, I want to pick up the object, I want to pick up the caterpillar from its ear, from its tail in this case, right? And we put it down in all kinds of different places, it'll pick up the caterpillar by its tail. You can deform it, you can change it, it'll pick it up by its tail, right? Just by having a correspondence function. Pick up from its ear. Okay, pretty good. Let's take a quick stretch. 7th inning stretch. That's what it should be called, right? The 7th inning. All right. So you should ask high-level questions or low-level questions, but is that landing? As these are different representations, they're fundamentally not just summarizing the state of the world as it's posed. And they're sufficient for control, but they required us to think about control a little differently down the pipeline, right? Yes?
So it seemed like those correspondences were on the surface of the object.
Yes?
Has there been work done where it's like volumetric? So I know like this point in the volume, and then if it's like clay and I reshape it, I know where that particle is in this new needed shape.
That's a neat question. So I'll repeat it for the people watching at home. But yeah, so the question is if these are always, all of the points we're registering are on the surface. In fact, when we make the 3D image, we're actually using the depth image to project our colorized, right? This is, the output of the network is an image in this case, and we are actually projecting it on the point cloud and spinning our camera around to make that image. And you say, could we do a volumetric version of this where you actually correspond into the body? I don't see why as long as you can you trust your reconstruction enough to talk about a penetrated point being the same in both cases, I don't see why you couldn't do that. I haven't seen it done. Have you guys seen it done? Did you do it? Is that what do you consider that to be in the neural descriptor?
Like a continuous, like a volume of descriptors
Okay.
instead of like an image of descriptors.
All right. Good. Yes.
Are dense correspondences the way, or what's the pros and cons versus the key points that you were doing for the categorical mode?
Yeah, awesome question. So are dense descriptors the way? I actually have seen people use them over and over again in lots of different applications. So there's a particular, the correspondence, they do pretty well. And I have seen that be successful. They don't have any semantic information. I was going to talk at the very end about just some of the things that are not here, right? So there's still, the notion of object is sort of still missing here. The notion of dynamics is missing here. So you could potentially train one per object, for instance, and have correspondences have a type of object. We did call it an object representation, but certainly like the dynamics of the object are missing, right? We don't know, and it doesn't tell you anything about the mass. It's not going to help you like crack an egg, right? It doesn't tell you how things are going to evolve.
That's missing the key points also.
Absolutely. Yeah, these both. I think. For both of these examples, it's absolutely missing from those, right? But for moving nearly rigid or possibly deformable, slightly deformable things around, it's a pretty powerful pipeline. I don't know that we've finished thinking about how to plan and control with it either, right? So there's work to do, even just thinking about the right way to consume that information, uncertainty in that information. I think it would, let's see, I've seen enough people use it, both of them. In various forms, people have implemented it in various capacities that I would trust that it would work, right? I wouldn't be afraid of saying you could grab the repository, grab some of your own data, and expect it to work, right? That's not the case of every tool we've played with, but this one seems pretty robust. Okay, yeah, so this is a class of just two examples of a big class, right, that I think is super powerful. I guess I forgot to show, this is the dense descriptors on that box pipeline I talked about before. It's interesting that it need not be, if there's symmetries, right, it could learn correspondence functions that are good up to the symmetries. You wouldn't expect it to be able to do better than that, right? But that's a super valuable representation of the object to go ahead and manipulate things. That's Greg, and that's our messy lab, yeah? This is Anthony's extension of it, which I hadn't thought about as a volumetric thing, but there you go. So neural descriptor fields, you should check it out. The emphasis in the title was about the SE3 equivariance, right? To be able to do relative coordinates, for instance. The video actually very nicely describes the pipeline. Still mugs on racks. It's the thing. It's pervasive in the field. Okay, so here's the. Let me pause that before I run it here. But yeah, here's the thing. So let's compare it. Remember, I said that at the beginning that we're not yet going to talk about. We're trying to do representations for the rest of our existing pipeline. And that is putting some sort of a constraint on our representation space, right? So what I'm basically saying is that we're taking RGB or RGBD or some combination in to our neural network. We've asked this question, and we said we're going to do it like a human-designed pipeline here. And humans are pretty creative, but somehow I think that is putting pressure on this to be interpretable in some ways. And the big thing that is, of course, happening is people are asking bigger questions now about what if I remove that assumption and use a learning backend, right? And you could ask, you can just say, I'm going to train end-to-end from my neural network right through my learning control. And the thing that's exciting about that is that really does remove this sort of, this requirement, right? That if it needs to represent uncertainty, then it will represent uncertainty in order to get the job done. If it doesn't need to, if it needs to represent something specific, only specific to a task, maybe it'll do that, only capture some relevant parts of the scene in order to capture the task. But the design strategies we have for these components are much, much weaker, right? So you end up using reinforcement learning or imitation learning. We'll talk about both of them. And they're not as generalizable, and they consume massive amounts of compute as these kind of planners. So I think to some extent this is a slightly artificial distinction, but what the field has done in the last few years is more and more people are just saying, I don't like this constraint. I don't know what the representation should be. It should be whatever the learning does, and therefore I must use learning control. And I think there's a lot more to do where you can have rich, possibly uninterpretable representations here and still do really good control over here. So that's a personal agenda for me, is to embrace learning control when it makes sense, but also remind people maybe that it's not the only way, okay? So we'll talk a lot more about some of the general approaches to control up here that could consume richer, possibly not just kinematic models of the state. And there's a big topic of learning state representations. So I would think, in answer to your question, David, I think these examples are some impoverished state representation that are sufficient for some kinematic tasks, right? But they're a impoverished notion of what the state of the world really is, right? Like I said, cracking an egg is just an extreme example, right? But or boiling, I don't know. You can imagine a bunch of things which have a lot more state than just its current positions as specified through the correspondences, right? So thinking about how to find those richer representations and writing, learning or writing controllers around them is a big agenda. Okay, so when we do imitation learning, we found in our lab that using these dense descriptors as a pre-processing step in order to then train a neural network policy does work incredibly well. So this is just taking those same examples where we're using the dense correspondences. For instance, on the hat, I'll tell you more about this when we talk about imitation learning, but it turns out that if you just sort of give to your learned policy a handful of key points on the hat trained through dense descriptors and ask it to then, put hats on the rack or learn controllers that can move plates around and do more dynamic tasks, it's been surprisingly good. Okay, so we'll talk about that in the imitation learning section. And I really think this is just two examples of a big class of approaches that are thinking about novel representations for the geometry. One that I like from Andy Zhang and company is they do this transporter nets where roughly they're saying, there's a lot of interesting things happening in the paper, but maybe at the high level, what they're saying is that my assumption about the dynamics is when I grab these pixels, those pixels are all going to move together, okay? And that allows them with a rich pipeline to sort of do incredibly general and useful tasks for picking random unknown objects and putting them into bins and things like that. Just from looking at the raw perception, having a model that if I pick here, those things are going to transform through a standard rigid transform into the new place, allows me to do a lot of rich tasks. So the deep perception world is alive and well. It's moving super fast, and I think you'll find many things that will change the way we should program our robots. Good. I'll end a few minutes early, I guess, and I'm happy to stick around and answer questions for projects.